Okay, we're recording. So here's a list of some of the important topics that hopefully you guys should be able to kind of conceptualize in your head and understand. So solubility, so which we're familiar with, molar mass, which is you're gonna see is just bouncing back between like different values or like different like ways of measuring things. Molality, some laws, some colligative properties, and osmosis and I. So yeah. So there's some important equations that we're going to need for this module. So we have molarity, which is moles of solute over liters of solution. Not to be confused with molality, which is moles of solute over kilograms of solvent. Molality is denoted by little m, whereas molarity is big M. So try not to get confused with that. We also have density, which you guys should know. You guys have been doing density since time immemorial. So grams per ml, and mole fraction, which we've done mole fraction before. So the mole fraction of A is equal to moles of A over total moles. So that's mole fraction. And really we're going to be focusing on, you'll be given like 2 of these and you'll have to solve for the other 2. You'll be given like 1 of them and you solve for the other one. So hopefully you guys should be able to do that by the end of this PowerPoint. So let's do a practice problem. So we have the percent mass of compound A, and it gives us our molar mass, is the molar mass is 130 grams per mole, and the percent mass is 20%. It also gives us our density. So the density of the solution is 2 grams per milliliter. And it tells us to find big M and little m, so molarity and molality. And then let me just change something real quick. All right. So it gives us our density as well. So we have the molar mass, density, and the percent composition for this problem. So the first thing we want to do when approaching a problem like this is to assume we have 100 milliliters of the solution. And then once we make that assumption, everything else we could kind of calculate and kind of just come to the conclusion on. So I was planning on using my iPad here, but it seems my iPad is dead and doesn't really want to work right now. But so I'll just use this with some text. I'll change this to. So yeah, so we could get all of that good stuff by, so we have 100 milliliters, and based off of we assume we have 100 grams of solution. So 100 grams and 100 grams. So if we have 100 grams of the solution, how much would you say is our compound A? If 20% is A.
20 grams.
Mm-hmm. So we could say we have 20 grams of A because 20% of 100 is 20. And if we have 20 grams of A, it makes sense that we have 80 grams of water. And if we have 80 grams of water, we also know that we have 80 milliliters of water because the density of water is 1/1. So we can assume from assuming that we have 100 grams, we can get that we have 20 grams of A. Hello. So yeah, 20 grams of A, 80 grams of water. So we go on to the next step. Once we have the 20 grams, we could calculate for moles of A. So we do 20 grams times the molar mass, which in this case is 130 grams per mole. And we can find that we have 0.15 moles of A. And after we calculate moles, we could also calculate the volume based off of our density. So we know that we have 100 grams of the solution, and we know that for every 2 grams of solution, we have 1 ml. So we could then say 100 grams multiplied by the density to find our volume. So it would be 100 divided by 2 gives us 50 mLs. So all the solution is 50 mLs. The next thing that we could kind of do is just plug in for either molarity or molality. So in this case, we went with molarity first. So molarity equals moles per liter. Therefore, molarity equals 1.5 moles divided by 0.05 liters. And we get 3 m, 3 molarity, 3 molar. And we can also solve for molality, and that's moles per kilogram of solvent.
Masha is asking how you got the 0.15.
Yeah, so we know it's moles per liters, and if we have 50 mLs, we could convert that to liters, just move the decimal 3 spaces to the left rather, and we have 0.05.
No, the 15.
Oh, 15. Yeah. So let's go back to this one right here. So we already determined that we have 20 grams of A because of the percent composition. We assume that we have 100 grams, and if 20% of that will be A. So we have 20 grams of A, and we're going to use the molar mass given to us in the problem and say that 130 grams is equal to 1 mole. So if we plug this into the calculator, 20 divided by 130, we get about 0.15 if we round down mole. And that's where I got the 0.15 from. All right. So then we just plug it into the equation. And then same for the molality. Yeah. So we have 80 grams of water. we end up with our molality, which should be little m. So not big M, but little m. All right.
Can you go back to the molarity slide for 1 second, please?
Yeah.
Thanks.
Are there any questions on this right here?
I have one. Like, where did you get the 50 milliliters of water?
Mm-hmm. So we assume that we have 100 grams of the 100 grams of the solution. So given the density, we know that for every 2 grams, we have, we have,
Oh, okay, so you just divide. Okay.
yeah. Mm-hmm.
Yeah, I was just about to ask you to put it on the molality slide.
Yeah.
Yes, thanks.
You know, where's my... So yeah. So I did include a little breakout session so we could do some a problem all together. So I'm gonna go ahead and give you guys put you guys into some breakout rooms, and if you go to page 119 in your workbook, I would like for you guys to try and do practice exercise number 1. So yeah. Does anybody have any questions before I give you guys into your breakout rooms? Oops. No? Alrighty then. I don't have a book now. Hopefully someone in your team will have it. If not, I will join your breakout room and then give it to you right there. So let's see.
Maulam,
Let's do
ahí voy.
3 rooms. Alright. So I'm gonna go ahead and open the breakout rooms now. Ready. Hello, everybody. You guys want to see something cool? Check this out. So the problem is, let me see. I can put it on the screen for you guys. So 15% mass. So sulfide in water. Find molality. So that's the problem. So yeah. Hello, everyone.
Hey,
Hey.
Are you guys doing well right now? Any questions on the problem?
no.
Not yet.
Alrighty, cool.
So for the kilograms of solvent, we used what do we use?
0.085 because it's 85 grams divided by 50,000.
Thank you.
Check out my new cat.
Mm.
What's his or her name?
His name is Marcus.
Really?
My name. Mm-hmm.
Marcos. That's funny.
I love cats, but I'm really allergic to them. So
I'm like allergic to, but not like terrible. So like I
no,
just
I'll
sneeze.
die.
At them.
Did you get 2.26 middle M?
Yep.
Okay, cool. Thank you.
Mm-hmm.
Cool, you guys solving stuff. Let me go check on the other groups.
Okay.
Um,
But we don't have the density here, so we don't have to do that. So I'm thinking what we do now for molarity, for molality, it's number of moles divided by kilograms of solvent. So all we have to do, we have the number of moles, so now we just convert, because the solvent is sodium sulfide, right?
Yes.
Okay, so I'm thinking we divide 78 grams by 1,000 to find it in kilograms. So, oh yeah, sorry, 15 grams to divide it, to find it in kilograms. So that would be 0.0, is it 0.0015? Because I'm doing it in my head, I'm sorry.
so
0.015, I think.
0.015.
so I just joined, but
Kilograms?
Yeah. So Marco, the first thing we did, we took the 15% and we wrote that as 15 grams of sodium sulfide. So we have 85 grams of water, right? And then we took 15 and divided by 78 to find the number of moles. So we got 0.19 moles, right? So now for us to calculate the molality, do we just divide the 1.9 moles by converting the number of grams to kilograms, and then we divide it by that, and that gives us the answer?
Yes. So you found the moles of sodium sulfide, right?
Yes.
Okay, and then yeah, you just divide that by the kilograms of solvent.
And the solvent, oh, the solvents. So we divide it
forget.
we convert 85 grams to kilograms then? Or is
Mhm.
it 15? Okay, so 85 grams to kilograms. If we divide that by 1,000, it's going to be 0.085. So we would do 0.19 moles divided by 0.085.
I got 2.23.
So it's approximately
Me
2.23.
Mhm.
So
You got that.
approximately
Yeah.
2.23 molality. Is that correct, Marco?
Is it 2.23 or 0.23?
We got 2.23.
2.2.
0.2. Yeah, I mean, I'm counting on you guys to solve it. So, yeah, if you guys are good, I think you could head back to the regular room.
Okay.
Okay.
How do we head back?
I think it says leave
Yeah.
room.
Okay, leave room.
Okay.
Alrighty. I'm not too sure if that was ended up being 10 minutes, but I think we'll be fine. Alrighty. So, to wait for everyone to come back. It looks like everyone's here, minus Alexis. She'll be here. She'll be forced to be here in like 20 seconds. So, what did you guys get? Go ahead and put it in the chat rather than say it out loud, because I don't want everyone to speak all at once and for someone to get spoken over. So if you want, you just put into the chat what you guys got. So 2.23, 2.23. 2.23, 2.23. So it looks like really all of you, from what I could see here, got 2.23 molar. Don't forget to write your units. So it'd have to be big M. Little m is, oh no, little m. Because we're looking for molality. So all these are right. Just don't forget little m will denote molality. So yeah. Any questions on this practice exercise? What to do, what not to do? Anybody run into some trouble or not? You can speak now.
I have a question. So the one on the bottom, the solvent will always be the higher percentage, right? For the kilograms?
Yes. Yeah, for the most part. You can have like well, yeah, it would have to be the larger one, because once the other one becomes too big, then you're kind of dissolving the smaller substance in the larger substance. But yeah, the solvent will always be the larger thing.
Okay, thank you.
Alrighty. Cool. If there are no more questions, let's go ahead and jump back to my PowerPoint. Okay. So we just did this slide. So, uh-oh. Okay, so let's go to the next slide. Oh no. Okay, so this one, I got a cool little animation for you all. So colligative properties. So hopefully you guys have heard of colligative properties up until now. They're properties that are dependent on concentration. So different things that could change are vapor pressure, the boiling point, the freezing point, and osmotic pressure can all be changed by the concentration of your solution. So basically, a change in stuff, in the concentration of stuff, will give you change. Wow, very beautiful. So yeah, Henry's law. So this is a equation that is used to relate concentration to pressure. So C is our concentration, K is a constant, and P is pressure. So if you kind of just ignore the K, you can see C is equal to something P. So they are directly related. So let's take our knowledge of like kind of algebra and just kind of like break it down a little bit. So if we assume that Henry's law is obeyed, if I were to increase the pressure of a gas over a liquid from 0.1 to 1.0 atmospheres, how will the concentration change? And let me rewrite the equation here. Let's see. So what do you guys think? If the pressure of a gas is changed from 0.1 to 1.0, how will the concentration change? So what kind of change are we seeing in these two numbers? Is it being doubled? Is it being tripled? Is it being multiplied by 5?
Isn't it being multiplied by 10?
Mm-hmm. So it's being multiplied by 10. So if we have a multiplication by 10 here, what do you think will happen to C?
C will also be multiplied by 10.
Mm-hmm. C will also increase by a factor of 10. And that's kind of I think a good way to really understand Henry's law and how concentration and pressure are related in that way. So are there any questions on Henry's law? I don't think I have a practice problem for you guys to do.
So what will be the constant in that situation?
It depends on the problem. The constant will most likely be given to you, or you have to solve for it.
Okay.
But in the case of this thought exercise, the constant is just there.
Okay, got you.
Mm-hmm. All right. So let's go to the next slide. So I don't think this is Henry's law anymore. I think this is Raoult's law. So yeah, not Henry. Raoults. So this is Raoult's law now. And this is non-equation used to relate concentration to pressure. I think I messed up on this slide. So this is an equation. Oh, okay. So this is an equation that is used to find the mole fraction or the partial pressure of a gas on a liquid. So you can see here on the right side, I've written the P naught of A. That little circle means like not. So the pressure of pure substance A is PA naught. And then XA, mole fraction, which you guys should be familiar with. And then PA, which will be the pressure of A once all of it is solved through. So, let's jump to the next slide. And let's do another breakout session. I'm trying not to break out sessions a little bit more. Let me know if you guys prefer to not have them. But yeah. So here I'm giving you guys a problem. So determine the mole fraction of acetone in a solution of acetone in water if the vapor pressure of acetone changed from 750 milligrams of mercury to 735 millimeters of mercury. And I give you guys a little hint there. So 750 millimeters of mercury is the vapor pressure of pure acetone. So yeah. So P naught of A is going to be the 750. So yeah, any questions before I break you guys up? This one, I'm not going to leave you guys in there for too long. It should come pretty quick. So yeah, let me give you guys to your breakout rooms then. All right. There you go. You guys are good to join.
You get 1.02.
No, it's 0.98.
Oh, I did it the other way around. Mhm.
For the partial fraction, you always need to have like a number less than 1, always.
Mm-hmm. I agree.
Okay, cool. Thanks.
So what did you guys get for your final answer?
0.98.
0.98. All right. Cool. If you guys want, you can head back to the to the other room. I'll go check on the other people. How goes it, everybody? Why are there penguins on my screen? 0.98. Mm-hmm. That's what I got as well. So yeah, you guys solved it. So you can head back to the. It's going well, I guess. So yeah, you guys could go ahead and go to the larger room if you guys want, and then I'll check on this final group. Hello, everybody. How goes it?
Okay, guys. So it's terrible right now. It's terrible, but XA equals because I'm looking back at the notes. XA equals moles of A divided by total moles.
Yes, but don't
That's
forget
what-
we're looking for mole fraction. So we're looking for XA. We're not necessarily looking for moles or total
Damn
mole.
it!
Yeah,
I'm like trying to figure it out. So
I think you may be overthinking it.
all right, so we know P of A is 750 millimeters per is millimeters mercury, right? And then
Mhm.
there's a difference. It goes from 750 to 735, so there's a difference of 15. Would that be negative 15? Or is it
Well,
still positive 15?
you're right that there is a difference of 15, but keep in mind that we're not really looking for a difference of anything.
Okay.
We just plug in.
That's only for the colligative properties, right? That you're looking for the difference.
I don't think even then.
Because I was thinking about what you did where we found a difference of 10 and you multiplied it to both sides. For the colligative for Henry law where it's C equal KP.
But this is a
So I
practice problem for
think I
Raoult's law.
confused it. Yeah, I'm sorry about that.
Oh no, you're good. So let me take you guys to the main room and I'll explain it.
Okay.
Alrighty. So let's see. I think everyone's back. Okay. So let's go ahead and take out the whiteboard and see what's going on here. So we know that our equation will be P of A is equal to the mole fraction of A multiplied by the pressure of pure substance A. And it's given to us that our pure pressure is 750. And our final pressure, after everything is diluted and everything, is equal to 735. And it's asking us to solve for mole fraction. So we could rearrange this using our big algebra brains to say that XA is equal to 735 divided by 750. And once we do this quick division, we get what answer, you guys?
$0.98.
0.98. And
round up to 1.
well, you could round up to 1. It would make sense to, but then when you look back on it, it's kind of misleading because if you have a mole fraction of 1, that means you have 100% of, like, it's basically, you're implying it's a pure substance, if that makes sense. So you may want to keep it as 0.98, just so you don't really confuse yourself. Does that make sense?
Okay.
Yeah. All right.
Yeah. And what's the unit if there's one?
So there would not be one because we have millimeters, mercury, millimeters, mercury. They both cancel.
Okay.
And then mole fraction is moles over mole, and those cancel as well. So your mole fraction would just be
Okay.
0.98. So yeah. Any questions on this kind of stuff? It's not too hard, I don't think. Not impossible. So yeah. That's Raoult's law. So let's go ahead and jump back to my PowerPoint. So yeah, this is Raoult's law, not Henry's law. Raoult's law. All right. So now let's talk about electrolytes and non-electrolytes. So hopefully you guys can recall from lecture that electrolytes are substances that fully dissociate into ions in water and can carry an electrical current within them, between them. And an example of an electrolyte would be NaCl. When we introduce NaCl into water, we see that the chlorine will come off, become Cl minus, and our sodium will gain a positive charge. And because there's a difference in charge, electricity can flow between ions, as opposed to non-electrolytes. So non-electrolytes will not dissociate into ions, therefore cannot carry an electrical current in them. So I've given you the example of glucose. So you may be thinking to yourself, I've dissolved sugar in water before. Why isn't it an electrolyte? So while glucose in this example may be able to dissolve in water, it doesn't necessarily dissociate in water. So just because it dissolves doesn't make it an electrolyte. It could still be a non-electrolyte. So yeah, any questions on electrolytes or non-electrolytes?
Yeah. So Marco, I get what you're saying. So what you're saying is that if if ions dissolve in water, but there's a electric charge, then it's an electrolyte. But if glucose, for example, dissolves in water, but there's no charge present at all, then it's not an electrolyte. Is that
Mhm.
what you're saying?
Yes.
Okay.
Yeah. All right. Let's jump to the next slide then. So the next slide is the Van Hoff factor, denoted as lowercase I, not to be confused with I from like calculus or something like that. And what this factor refers to, which is also called the ionic strength factor, is how many ions are present after dissociation. So I got a cool little animation here of H3PO4, so phosphoric acid. And we know phosphoric acid, I'm pretty sure, is a strong acid, so it'll dissociate completely in water. So knowing that, we drop it into some water, and then check this out. Whoa. So then it dissociates into its respective ions. So how many ions can you guys count are on your screen right now?
Be 4 in total.
Mm-hmm. So before, so each of the hydrogens, 1, 2, 3, as well as our phosphate. So it will have 4 ions. So our Van Hoff factor will be 4. And then check this out. This is even cooler. Oh wait. Oh snap. It came from fire, you guys. That was so cool. So yeah, I in this case would be 4.
And yes, is Kate. He's
Oh.
quaking.
What'd you say, Paulo? Sorry, I couldn't hear you.
The movie editors are quaking.
That's right. So yeah, Van Hoff factor in this case would be 4. So I got some practice here, and I won't do the breakout rooms because these should be pretty quick. So let me just call on some people. Let me pull up the list of people. So yeah, Delianne. 2 questions. One, what is I for this first one, HCl? And the second question is that how I pronounce your name?
It's 2, and you can say it Dilean. Dilean.
Or how do you pronounce it?
Dilean, like that, just Dilean. Or you can call me Dili. It's easier. That's how
Okay,
people
I think I'll
use.
go with that one then.
Yeah.
Okay, and what'd you say I was? I wasn't listening.
2.
2. Mm-hmm. So HCl, strong acid, will dissociate into 2 ions, H plus and Cl minus. Alrighty. Michelle, what about that bottom one, NaCl?
For the bottom.
Mm-hmm, the bottom one.
Excuse me, can you please repeat the question?
What would be the Van Hoff factor for NaCl?
Oh. I'm not sure.
So we know
Sorry.
NaCl.
I'm confused.
Oh, I'm sorry.
I'm confused. Can you please help me?
Yeah, of course. So we know NaCl will dissolve in water, and when it dissolves, it'll carry the electrons onto the Cl, and our sodium will become positively charged. So the Van Hoff factor really is how many different ions do you see here in this box?
One.
So pretend they're split apart. It's kind of misleading.
So it will be 1. Or
So close. So we have a negatively charged ion over here. And then right here, we have a positive on the left. So if we have 2 different ions, then we could assume that we could determine that our Van Hoff factor will be 2. It would have been better if I had showed them splitting apart. But yeah. So in this case, our Van Hoff factor would be 2.
Okay, thank you.
Mm-hmm. So let's see. Masha, what do you think about this one up here? Our carbonic acid.
Carbonate is CO2 minus. Yeah.
Carbonate is CO2 2 minus.
Minus CO2 1 minus. Yeah.
Let me see. I thought it was.
Okay.
All right. Well,
CO2. Yeah.
I think
Okay.
you're right.
Mm-hmm.
kind of did this kind of late. I think I might have been
Mm,
snoozing off.
mm.
But let's just say for the example that I have here on screen,
I think
oh yeah, 2
2H and carbonate is 1.
minus. So we'd have 2
Yeah,
hydrogens and then 1 carbonate.
one carbonate. Yeah,
So what would our Van Hoff factor be?
I think it is 3.
Yes. So it would be 3. So we have 1 H plus, our carbonate ion, and another H plus for a Van Hoff factor of 3. And then lastly, we have glucose. Glucose doesn't dissolve into any ions. So Pablo, what would our Van Hoff factor be for glucose? Hey,
I'm gonna say 6, but I don't
so remember glucose doesn't
because
dissolve
I don't know
into
if the
ions.
carbons are linked together with the. Oh. Say what?
The glucose doesn't dissolve into any ions. It stays as one unit.
Oh, okay, okay.
So yeah, if it doesn't dissolve into ions, our Van Hoff factor would be 1. And it's 1 because it. So you think of it like how many groups are left. In this case, it will stay as one single group. So the group would be 1. Oh. Alrighty. So now we're talking about boiling point elevation. And boiling point elevation, which is also one of the colligative properties, we can see by these 2 different equations. On the left here, we have the change in boiling is equal to I kBm, where K is a constant. We have little m here, so molality, and I is Van Hoff's factor. And using that change in boiling point, the change in boiling point factor, we could plug it into this second equation here to determine our final boiling point of a pure substance that has some stuff added into it. So our boiling point temperature is equal to our boiling point temperature of the pure substance plus I kBm, or plus the change in boiling point. And you can see elevation. So almost always we're going to have an increase in boiling point. You kind of think of it as, so water has all these different intermolecular forces. And when we add some stuff in, there's going to be an increase in intermolecular forces. So it's going to be harder to break all those bonds, and the boiling point will elevate, to kind of tie it back. So yeah, those are our 2 equations. And also also when we talk about boiling point elevation, we also talk about the freezing point depression. And I kind of lacked it on this one, but it's the same as boiling point, but we're talking about freezing. And there's one important change. So the important change is the inclusion of a minus sign, as opposed to elevation had a plus. And if you think about it, it shouldn't be too hard to remember, because we know freezing point depression, we know depressions insinuate that we're going down. So it would make sense to have a minus sign as opposed to the plus. So yeah, K is our constant. Each substance has its own K, KB, and KF. And yeah, those are our two equations for freezing point as well as boiling point. And I think next I have osmosis. You guys are going to be really impressed with this one. So osmosis is solutes from a high concentration moving to a lower concentration through a semi-permeable membrane. And it's like a lot of big words, but really the main thing is when given the chance, if you have two different solutions, they're going to mix until they become the same concentration. So we can see on the left side, we have 3 molecules of A, and on the right side, we have 7. So there's an imbalance. So there's going to be like kind of a tug of war type thing until balance is achieved. So A is going to move over so that there's 5 on the left, 5 on the right. And that's basically osmosis. For the purposes of this class, really we're just going to be dealing with the math of osmosis. So yeah, and osmotic pressure. So osmotic pressure. So pi is a symbol for osmotic pressure. And the symbol in this case has nothing to do with the mathematical value of 3.14. So no connection. It's just a symbol that we use. So pi equals the Van Hoff factor multiplied by molarity multiplied by R, or our gas constant, multiplied by T, which is just temperature. And if you could remember, R is in, I think, grams per something per mole or something like that. It's let me see if I can write it down for you guys. So R is written as liter atmosphere per K mole. So you'll notice we have K here, so Kelvin. So because we have Kelvin there, our temperature is going to have to be in Kelvin. R is in Kelvin, so T must also be in Kelvin. So I think this is all I have.
Marco, could you explain that one more time, the last part that you did?
Yeah, so
The part that you drew out. I'm sorry.
yeah, no, of course. So R is our gas constant. So R will never change. And R is equal to 0.0821. And then the unit is liter atmosphere per K mole. So, knowing this, we can see that if R is written in terms of K, once we do all the calculations, T must also be in K. That way, the K unit of T will cancel this. M, which is in moles per liter, will cancel out the moles and the liter. I doesn't have any units, so all we're left with is atmosphere, which should be correct because we're looking for osmotic pressure. And that's the importance of having our temperature in Kelvin.
Thank you, Marco.
Mm-hmm. So, man, we kind of sped through this one. Yeah. So I'm going to clear the screen. And I do have these two practice problems that I would like you guys to do in your breakout rooms again. Would you rather us do them here as a class, or are you guys liking the breakout rooms? Just a quick question.
Let's do them as a class.
You like to do them as a class? Okay, yeah. Okay. So let's do them here then. So we're looking for workbook page 128, number 2. So let me jump there real quick. Page 128, number 2. Alrighty. So let's do it. So on page 128, number 2, it tells us the solution of a 7.89 gram calcium hydroxide is being mixed into 500 grams of water. So it gives us our KB, our KF, and it's asking us to determine the boiling point and freezing points. So how are they going to change? So let's look at boiling point first. So the first thing I would recommend you guys do, since we know we're looking for boiling point, is to write down the equation for boiling point. TB equals T naught B plus IK B M, where M is little m. And from here, we could just plug stuff in. So we could plug in whatever is known. So what is the normal boiling point of pure water in Celsius? Mm-hmm. 100. So we could plug that in. So TB equals 100 plus what about I? What would I be in this case? Calcium hydroxide.
Wouldn't that be 7.89 grams?
So keep in mind, we're trying to solve for I here. So the Van Hoff factor.
Oh, I'm so sorry about that. Sorry.
Oh no. So Leslie says 3. Sophia says 3 question mark. So Leslie, why would it be 3?
Is it because CA has it's what is it? Where am I? Okay, hydroxide is a OH, like the ion is OH negative, and Ca is Ca2 plus. When you put them together, you get CaO2, CaOH2. That makes sense.
Yeah.
Sorry.
You got that. So yeah, exactly correct. So Ca has a charge of 2 plus. And we know that OH has a charge of just 1 minus. So when we come up with our molecule, we're going to need 2 hydroxides. So it'll be CaOH2. So that's where we get the 3 from. So we could plug in I, 3. KB is given to us. It's 0.512. And finally, molality. What's our molality in this case? So it's given to us how many grams we have of the solute. So calcium hydroxide is our solute. So we could just convert that to moles. So 7.89 grams, and then something grams is equal to 1 mole. Does anybody know the molar mass of calcium hydroxide? Has anybody solved for that? Someone want to give me an answer? So let's see. Oxygen, 16, 32, 34, 34 plus 40, 74. So 74 grams will give us 1 mole. Let me just double check that. 74.009. In this case, I'm just going to use 74. But yeah, 74.09 would also be good. So knowing this, we could just divide to see how many moles we have. So 7.89 divided by 74. Which comes out to 0.1. It's a nice number. 0.1. We can use 0.11. So now that we have all this written out, I'll get rid of this real quick. Give me some space. Now that we have all this written out, we can now just solve through and look for our new boiling point temperature. So someone wanna solve through and then shout out the answer. Yeah, so it'd be 100 plus right here is about 0.17. So if you just round up, it'll be to 100.17. So not too big of a change, but a change nonetheless. And that's only half of the problem. So we know we're also going to be looking for the freezing point. So if everyone's good here, I'm going to clear the screen. All right. So
Is there a unit for this or not?
yeah, so it would be Celsius because
Celsius, okay.
our KB is in degrees Celsius per kilogram per mole. And molality, let me see that. The M was in molality. Why didn't we divide by? Oh, you know what? That's right. Yeah. No, you're right, Sophia. Yeah, you can go ahead and go, Masha, if you need to. So Sophia made a good point. So we're using little m. So we have molality. And we solved that we had 0.1 moles of our calcium hydroxide. And we forgot to put the the other part of molality. So we know that molality is this over kilograms of solvent. And in this case, our solvent is water, and it tells us we have 500 grams of it. So we would divide the 0.1 divided by 0.5, because we're changing grams to kilograms. So our molality number will be 0.1 divided by 0.5. 0.2. So in this case, little m would be equal to 0.2. And then there we could plug in 0.2 multiplied by 0.512, I believe, multiplied by 3 plus 100 equals TB. And TB will be, see, 1, 3, I believe 100.512 times 2 times 3. So TB will be equal to 100.31. So yeah, good catch, Sophie. This would be our new boiling point temperature. Any questions on that part of it before we move on to the freezing point?
Where did we get the 0.5 when we divide it?
Yeah, so if we read the question again, it tells us that we have 500 grams of water. And we know molality equals,
Oh, okay, yeah, the kilograms, yeah, sorry.
yeah, per kilogram solvent. And that's where we get the 0.5 from. So let's go ahead and move on to the freezing point then. So we could remember our molality will stay the same, 0.2. Our Van Hoff factor will stay the same. Will continue to be 1. And our T boiling point will not stay the same, because now we're looking at freezing. So I'm going to erase all this. Without clearing everything.
So is I not 3 for this one? Is it 1?
Oh, no, yeah, you're right. I don't know where I got 1. I will continue to be 3. So yeah, so freezing point, we know basically the same thing. Temperature freezing equals TF, our pure substance, minus IK.
I got the answer already, Marco.
IKF, little m. So yeah, we just plug everything in. We know our freezing point of pure water in Celsius is 0.
I got minus 1.12.
Minus 1.12. That sounds about right. And then 3 KF is 1.86. And then 0.2 equals TF. And in this case, TF would be minus, you said what? Negative 1.12?
Yes, sir.
Alrighty. And it would be in degrees Celsius. So yeah, that's a freezing point. Basically the same thing as boiling point. It's just important that you remember the negative sign. So any questions on boiling point, freezing point? Not too hard, right?
Not too hard.
Alrighty, cool. So let's do this second part. So page 132, problem number 2. Yeah, I don't think this module is not too long, so we kind of have a lot of extra time to kill. But yeah. So practice problem number 2 on page 132 tells us calculate the osmotic pressure exerted by the following solutions. So we have 12.3 grams of aqueous sucrose in 3 liters of solution at 65 degrees Celsius. So we know we're looking for osmotic pressure, so it would make sense to write down the equation. So I equals I MRT. I big M R T. So knowing what we know, we can plug in some things. Sucrose will not dissolve into ions. So we know I will be 1. I equals 1. Now the next thing we're looking for is big M, so molarity. What would our molarity be in this case? So it's given to us in grams. So we have 12.3 grams of sucrose. C12H22.
Wouldn't that be divided by the total molecular mass for sucrose?
Mm-hmm.
Okay, so I already calculated that is 342.176. So just 342 on the bottom.
All right, 342 grams will give us a mole. So how many moles do we have?
I got 0.35 or
0.35.
0.036.
Okay,
That's what I got.
so 1 right here. So we got, 0.36 you said?
Yeah.
You said it's 0.036?
Yeah, I think.
Oh,
If
0.036?
someone can fact check. Yeah.
Okay, yeah. I was about to say, because I thought 0.36 seems a little bit too much. Okay, so 0.036 will be our molarity. Now, next we plug in our gas constant. So what would our gas constant be in this case? Or in every case, really? So if you don't know, it's in the front of your book. It's on the back of the title page.
0.08 something?
Mm-hmm. 0.0821. And then finally, we have temperature. So what would our temperature be in this case?
65 degrees Celsius.
Divide the moles by 3. Oh yeah, you're right again. So we have 0.036 moles. Man, 0.036 moles. But we're looking for molarity. So it's given to us that we have 3 liters. So that's that. And then we divide by that. And for our molarity, we would get, what would we get? 9, 18, 9,
0.012.
0.012. So that would be our molarity. I'm sure you guys know, but I just woke up. I'm just kidding. So 0.012. be our molarity. I'm just kidding. I did this all on purpose so you guys could catch my mistakes. So yeah, so all we have left to solve for is temperature. So what would our temperature be in this case? If we have 65 degrees Celsius. How do we change from Celsius to Kelvin? Leslie says 338. Let me see.
Wouldn't it be plus 273?
Mm-hmm. Yeah. So we would just, so Kelvin equals Celsius plus 273. So Kelvin in this case would be 338. So once we have all this, we could just solve for osmotic pressure. So it'd be 338 times 0.2 times 0.036. Oh no. Oh man. Yeah, you're right. I erased the wrong thing. I'm falling apart. Pi equals 1 times 0.1012 times 0.0821, 338. So pay no attention to this top one. So we're going to use that bottom equation. $338. So what'd you guys get for your osmotic pressure?
It is 0.33.
Mm-hmm. Yes. So it would be 0.33. About. Atmospheres. So yeah, that is osmotic pressure. Module 5's math is mostly focused on just kind of plugging stuff in. So I hope this math wasn't too difficult. But yeah, any questions on like the osmotic pressure or really anything that was covered during this module? No. All right, cool. If there are no questions, then how would you guys like a quiz? A post-exam quiz. So, I like the idea of that. So yeah, let's do a quick quiz then. You guys could work as a class for these first couple problems, and then yeah, we'll see where we go. So I don't have any questions lined up, but let's see. Let me go to cut that. Give myself a blank slide. So let's see. If I were to give you this right here, so chlorous acid. Can someone tell me the Van Hoff factor of chlorous acid?
Give me a second. Let me think, Marco. Hold on.
Okay. Looks like we got a 3. Someone said 2.
Wouldn't it be 3? Because it's ClO. No, it's HClO2.
I don't know. It's not a quiz for me. Ask your peers.
Piers, is it 8ClO2?
Ask Marco, he knows.
I do know. So some people saying 3, some people saying 2.
3.
I said it's 3. I think it's 3.
I believe it's going to be 3 since O2 is dipole. Yes. 3 question mark. 3. So I see mostly 3s. So does everyone here agree that it's going to be 3 then? Are you sure?
Stop trying to trick us, Marco. Is it 3?
So Dilly, why do you think it's not going to be 3? I believe you said it's going to be 2.
Because I think that you only have like 2 ions, the H plus and the chlorose ion.
Only have 2 ions.
I only have like a question. Like, it's that one is a strong or a weak?
This one would be
Wrong.
strong, I believe. But when we're
Then-
talking about the Van Hoff factor, we're not really thinking in terms of strength. We're thinking like hypothetically, if it were to completely dissociate, what would it dissociate into?
Okay.
Oh, isn't the formula? Oh, I'm sorry, Julian.
It's
Go
okay.
ahead.
No, you go ahead.
Oh, okay. The formula for chlorous acid is HClO, right?
So what does
I need to look it up.
OUS indicate?
There's 8ClO2, I believe, for that.
Alrighty. So if it's, I will tell you it's HClO2. If it's HClO2, think about my little diagram type thing here. So what would the answer?
Shit. So maybe it's 4 because you have HClO2. So Cl is surrounded by 2 oxygens and 1 hydrogen, so that makes 4. My bad. It's 4, right?
Colder.
No, because the chloric, is it chlorous? I'm confused on
You
that.
say
But
chloride.
that yeah, chloride. Oh my god, I can't think right
Chloride.
now. But doesn't that chloride? There you go. It just disassociates from the H's, so you're not left with the oxygens out, right? Just
Okay, I
the
see what you're
Mhm.
saying now. Yeah,
Mhm.
it's only two because of that, because it doesn't come apart. It stays together.
Yeah,
So
so
it's two.
it doesn't melt away. Just remember when you think about acids, they give up protons.
Got you.
So, what do you guys think? Final answer, 3 or 2?
Two.
Mm-hmm. So chess speaks for you guys, I guess. But the answer would be 2. The H would come off and the chloride will stay there. So yeah, that would be the Van Hoff factor of that. Let's see. Can somebody tell me clear all drawings. All right. If I were to give you so we have 25 grams of let me think. Sodium hydroxide in 700 grams of water. What would be our molality? You're not allowed in there. Come here.
I got this. I got this. I got this.
You guys think? Looking for molality. Later, Sophia. Thanks for all those good catches. Molality, little m.
I got 0.893.
0.893.
So the steps would be 25 grams divided by 40 grams will give you the number of moles. And then you take that number of moles and you divide it by kilograms of the solvent. So the given water is 700 grams. So you convert that to kilograms, will be 0.7. So you divide 0.625 by 0.7, and that will give you 0.893.
All righty. Yeah, sounds good to me. What about the rest of y'all? Does everyone agree that's the final answer? Looks like everyone's saying that that's the final answer. Would you say it was 0.9?
0.893, or in other words, 0.9, yes.
All righty. It seems that is also what I got. So 2 for 2. So these last 2 questions, I'm going to call on specific people. And you have to do as I say. So let's see. What do I want to call on? Melissa.
For the question that's on the board, the
Oh no, not the
25.
question that's on the board.
Oh,
I have a new question. Can you tell me a joke?
a joke?
A joke.
Um,
And if I don't laugh, you guys get deducted points.
Girl, you better make him laugh.
oh my gosh, I'm horrible at that. Okay. How do you tell if a vampire is sick?
How?
By how much he is coughing.
That's a
Okay, you
good-
laughed.
That's a good one. Alrighty. I like that one. Let's see. One more joke from somebody. Who should I call on? Melissa, who should I call on?
I got you. I just messed
On-
it up.
I don't know, Che. You answered these last two questions pretty well. I think I need someone else.
Pablo.
Pablo. On the spot.
What are you
just like
doing?
that.
Like this?
All right, hit me with the joke, Pablo.
Let me think. Dude, my jokes come natural. Like I cannot force them.
Was that it? That wasn't very funny, dude.
Okay, it's going to be one of. I don't think it's a good. Like you won't like it. I think it's offensive. But I'll say. It. Okay. Who are the? Who is the? No. Who are the fastest readers on the whole history of the world?
Who?
I'm sorry, I'm a horrible person. The 9/11 victims, because they went like 30 stories in
Oh, dude.
a few seconds.
No. Oh, man. I get it. I laughed. That was horrible. Oh, man. That was brutal. I don't know. Okay. I'll count that as a point for you guys. So, yeah. That's all I have for today. I'm going to stop recording here then.